All right, today's topic, math. So we're going to get into math a little bit more deeply. We're still not going to get into it as deeply as we would do in the computational math class that the QCB program offers. We're just going to get into it one step more than we did earlier when we were talking about it. Okay, I showed you this page one time earlier in the class. Let's talk about it just a little bit more in depth right now. So all the numbers represented in the computer physically in the central processing unit on the computer are binary numbers. So when you represent integers are straightforward, just sort of counting numbers. It's exactly the same as counting counting integers in decimal. It's just that the representation is a binary representation, right? It's just a different base. Right? So you can do base 2, you can do base 16, you can do base 10. It doesn't really matter. They're still exactly the same integer. When you start talking about fractional values, though, things get a little bit more complicated. And that's the main thing that we're going to just sort of briefly talk about today. You'll remember we had a homework problem that related to that a couple homeworks ago. So the fundamental unit of a number in binary is called a bit. That would just be a single, 1, or 0. So basically it's a digit in a decimal number. It's a digit in binary is called a bit. The next unit is called the nibble, which is 4 bits, representing numbers from 0 to 15 in decimal. Then you've got a byte, which is 8 bits. You can see nibble is half of a byte. Yeah, people always have a good sense of humor when they're writing, when they're developing computer technology. So byte, 0 to 255. Word, 16 bits, 65,000, and then a long word, 32 bits. While technically computers now are 64-bit machines, pretty much all computers that you run into nowadays are 64-bit. Typically with integers, you're still, the standard integer is still usually a 32-bit number, not a 64-bit number. So the range of those values is going to be limited from 0 to 4 billion. Or if you have sign, if you have positive values and negative values, then use one of the bits for that. So then it can go from minus 2 billion to plus 2 billion. So there have been issues historically where 32-bit integers were used for a lot of purposes, like if you're looking at some file on the hard drive on your computer, you have to keep track of where you are in the file. So if you read a bunch of stuff from the file, then you've moved to a new point in the file, and then you read some more stuff. So it has to keep track of where you are in the file. Originally, that file location was stored as a 32-bit number, but that means that if you have a file that's bigger than 4 gigabytes, then you can't keep track of where you are anymore. So there was a long time that you couldn't do anything with files that were bigger than 2 gigabytes or 2 gigabytes or 4 gigabytes, depending on whether you're using signed or unsigned numbers, because of that limitation. Now, it wasn't a problem for a long time because the biggest hard drive you could buy was, say, 500 megabytes. So you would never have a 2 gigabyte file, so it wasn't an issue. But anyway, so there are these gradual sorts of changes, so where things get shifted from 32-bit integers to 64-bit integers. For fractional values, we have floating point numbers, which are single precision or double precision. Technically, there's another type called double precision. They aren't really used very often. The processor in the computer itself knows how to do math for single and double precision floating point numbers. So in hardware, it can do things like sines and cosines and square roots and stuff like that of these floating point numbers. So it can do those things extremely quickly. The primary advantage of the single precision number over the double precision number is it's half the size, so you can store twice as many of them in the same amount of memory on the computer. Also, in some cases, that'll be faster. Other cases, they won't be faster. It depends a lot on the specific processor that you're dealing with. Single precision floating point numbers can represent values it's basically equivalent to 7 digits in base 10, right? So if you print a single precision floating point number in decimal, you have basically 7 digits of precision. Now, that means if you have 123.4567, the digits of precision include the digits before the decimal point. Okay, so if you try and represent a number in single precision, like So that represents 7 digits of precision. But if I have, right, that represents, how many did I type there? 6, 7, 8, 9, 10 digits of precision. So in single precision, you wouldn't be able to represent a number like that accurately. In double precision, you would. Double precision gives you 15 decimal digits of precision to work with. So for most purposes, that's completely sufficient. When you're working in Python, double precision is the standard. Whenever you have a fractional value in Python, it's represented as a double precision. And for integers, it defaults to these 32-bit numbers. And I mentioned in the first class when we talked about this, that Python has these built-in long integers. So if you ever use a number in Python that's bigger than the limits of the 32-bit integers, it will automatically turn it into this special type of object, which has unlimited size. It's just really, really slow. All right. Now this is back to what we were doing, that homework problem. 0.1 plus 0.1 is 0.2. 0.2 plus 0.1 is not 0.3. It's almost 0.3, but not exactly. So 0.2 plus 0.1, oops, and I typed a comma. There's a little bit of round-off error there. And you can see that the number of digits here corresponds to the number of digits in a double precision floating point number. If I try doing this, if I can use the built-in round method, and actually let's take a look at that. Help round. So round allows you to specify, to basically truncate a number to a certain number of digits. Now you have to keep in mind, though, that this is not magic. The representation internally after you do a round is still binary representation. So if you have a number which can't be represented exactly in binary, and you round it, it's still going to be exactly the same number. It won't help you. But if I do the sum first and then I tell it to round, then of course it'll get rid of this and it'll round it to the nearest decimal value. So that's why doing the rounding first won't accomplish anything. It's still not going to be correct. But if you do the rounding of the sum, then it will be correct. This is also just a good time to just quickly mention that when you define functions or you use built-in functions, Python supports named arguments. So all the functions we've been dealing with so far have just been positional arguments, meaning if you take one argument, you just provide the number, the value, whatever it is. If you take 2 arguments, then you give 2, and the order of those arguments obviously matters. But you can, if you have, say, 10 different arguments that a function might take, and sometimes the user only wants to provide 3 out of those 10 arguments, Python supports named arguments to get around that. So let's try this. All right. Now if I say f of 1, 2, 3, I get exactly what I'd expect. If I say f of 1, then I get these default values, right? So y has a default value of 10, and z has a default of 5, and z has a default value of 10. So if I don't provide those values, then it'll fill them in for me automatically. And I could also say f of 1, comma, z is equal to 3. Okay, so that allows me to specify x and z and skip y. So that's what we're seeing here in this round function. You can see the number, and it has n digits equals none. So if you don't specify anything, n digits defaults to none. If you specify something, then obviously whatever you specify is true. And if you want, you could specify the value by name. You don't have to in this case because there's only that one argument, so there's no real reason to use the name other than for clarity. So I could say round 1.234566 2, or I could equivalently say n digits equals 2. All right, so that's all just a little aside there. Okay, so the concept that we're seeing there is really no different than what you might see in decimal. So for example, let's say you say 1/3. Say you want to take 1/3 plus 1/3 plus 1/3. If you do that in decimal, but then you use this fractional representation, decimal notation, you'd say, okay, I'm going to do up to, say, 6 digits. I add 0.3333 plus 0.3333 plus 0.33, and I won't get exactly 1, right? There's a little bit of round-off error. Now, if I round it by 1 digit, then of course I'll get the right answer, but the actual precise number that you get is not going to be exactly 1.0. So computers, being literal-minded, if you say, is 1/3 plus 1/3 plus 1/3 equal to 1, it'll say, no, it's not equal to 1. Okay. Now, I will point out that if you say 1/3 plus 1/3 plus 1/3, that will give you exactly 1 in Python. Why is that? Well, here we do 1/3 plus 1/3. That's keeping it out to 15 decimal places, and it has sort of, you know, you'll still have that final ambiguity in the last bit. But basically, this is turning into, first it does this addition, so it becomes 2/3, right? It doesn't become 2/3; it becomes 0.6666, but it'll have the 7 at the end there, because the addition operation will take care of that rounding in the correct direction. So then the 3 and the 7 will average out, and you'll wind up with the correct value. So there are very specific requirements for how math is done on computers to give you answers which are as accurate as they possibly can be. The cases where you run into problems are with very specific values, like 0.2 plus 0.1. So the problem is that the way numbers, fractional values are represented in binary is the same strategy that's used for decimal, which is the values after the decimal point, or in this case the binary point, I guess you'd say, is a fraction of the position, right? So this is 1, 2, 4, 8, 16, 32, so on. And here, this is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, etc. So in decimal, that would be a tenth, 100th, 1,000th, 10,000th. So these fractional binary values are as good as decimal binary, fractional decimal values, but they are not the same as those values. So if you have a number, we'll just skip over this. If you have a number which can't be represented exactly like 1/3 in decimal, the set of numbers which you can't represent exactly in binary aren't the same set. So 0.1 can be represented exactly as a fractional decimal number, but in binary, that turns into a repeating fraction. And that's where we run into problems with the round-off errors, where the number really should repeat for forever to have a proper representation. So the conversion from the decimal fraction to the binary fraction is where the real problem is sort of occurring internally. Anyway, we'll talk about these issues in round-off error and stuff like that a lot more in depth in that other class. For here, it's just good to know that there are potential issues there, particularly when checking for equivalence of things that you're adding when they have fractional values. How do you get around that problem? Most of the time, it's not going to be an issue for you, right? I mean, usually you're just doing math and you're getting the value, and if there's something wrong in the 15th decimal place, who cares? A big place where this is a potential problem is in banking. So when you're doing banking, you have a certain number of cents, right? You have fractional values which are exactly 2 digits long. You can't have fractional cents beyond that, at least not if you're dealing with real currency. And if you have some sort of round-off error, which causes you add up a whole bunch of values and the sum is off by a penny, that's a problem. Because everything has to match exactly when you're doing things like banking. So there is a special library in Python called decimal, which will do exact representations of a specific number of decimal digits and won't have any round-off errors within those limits. It's a little bit of a pain to use, but the library exists. So if you're in a situation where you need to have where precision, decimal precision, is very important, that library is the place to go. There's also a library for dealing with rational fractions. So if you want to do things like add a bunch of fractions together and then simplify the fraction in the end, or turn it into a mixed number or something like that, the sorts of grade school sorts of things, but still sometimes useful in science, there's a library in Python called fractions, which will do that. Most of the rest of today, we're going to be talking about these other libraries, NumPy, Pandas, and SciPy. And these are large libraries of algorithms for doing various sorts of mathematical operations and dealing with large pieces of mathematical data. All right, so let's try another little test here. Basically, we're going to compute the sum of the sine of a whole bunch of values. And you can see here I'm using this single percent sign time it method to sort of time. So I'm defining a function. It's going to generate all the x values, then it's going to compute all the sine of all the x values, and then it's going to print. This is kind of silly, right? It's just going to print the last value in this list. It's not actually doing anything with the numbers afterwards. We're just kind of seeing what the last value is to make sure it's coming out right. All right. Okay, so we'll run that. You can see the star is still there, so it's still running. And there we go. So it took about 7.9 seconds. Now some of the, no, actually no, that should be correct. Let's do it one more time, and we'll just see if it still comes out with 7.9 seconds, or if it's a little bit faster. Yeah, about the same, but it's slightly faster. And this is the reason why sometimes you want to run these things more than once, more than one run, or more than one iteration. Because each time you run it, the computer may have been doing something, or maybe there was something that was getting initialized on the first pass, or something like that. Usually what will happen is if you do something like this once, it'll give you a time, and if you do it a second time, it'll be a slightly different time, and then if you continue, you'll see the second time repeating more or less over and over again. Because the first time you do it, often some sort of initialization is going on, like in this case, it's creating these arrays, and when you go back and you do it again, it's using some of the space that was already allocated the first time, so it's just slightly different. All right, anyway, so that took about 7.1 seconds. All right, here is another way you could approach the problem, which is ostensibly a little bit faster. So there's a module that's available for Python called Cython. Cython should be installed by default in Anaconda. If it's not, it's available as a module. And what Cython does is it translates parts of your Python code into C automatically, and it compiles the C code, and then it can run it at machine language speed on the computer. So it should make certain operations a lot faster, you would think. And it will make certain things a lot faster. So let's give that, oops. Sorry, you have to do this exactly right. So you have to put this load ext Cython thing in a block by itself first. You only have to do that once. And then the double percent sign Cython, whenever you have one of these double percent sign things, it has to be the first line in the block. Okay, so that took 3.8 seconds. Let's run it one more time again, like we did before, and we'll see 3.6 seconds. All right, so this took 7 seconds, and this only took 3.6 seconds. Now, if you look at what's happening here, so we're doing 50 million of these, making a list of 50 million values, and then we're doing 50 million sign operations. So that's a total of about 100 million floating point operations. Ostensibly, most modern processors are capable of doing more on the order of about 10 billion floating point operations per second. So that seems like it's not going as fast as it might. Now, one of the problems might be the fact one of the functions I'm doing is a sine, and transcendentals like sine and cosine, that sort of thing, take a little bit longer for the processor to compute than things like just adding two numbers together. So there are some operations which take a little bit longer, but that still, this is taking a lot longer than the CPU should need to take to do the amount of work that we just saw. So let's look at another solution to this problem. So Cython is a good thing to be aware of, but it's not used all that heavily. One of the issues is that you can't assume that if you're writing a program and you're giving it to someone else, you can't really assume that they're going to have Cython installed and set up on their machine properly. So it may cause problems for them if you're using it. So it's the sort of thing that people tend to use just themselves once in a while when they're trying to make something that's going to take a long time take a little bit less time. It may make things about twice as fast. All right, so now let's try doing the same thing, but we're going to use NumPy. Now, I mentioned before that it wasn't usually a good idea to use this from blah import star syntax, and there are some risks associated with it. You will very often see people importing NumPy as import NumPy as NP because it's a little more transparent and you know whether your methods are using NumPy or they're using math. But for the demonstrations today, we're just going to use this more convenient form. So I don't have to put NPs in front of things. Okay, so what are we doing here? I'll explain arange. Well, I guess we can explain arange is just like the range method that we've already dealt with in Python, but it will work with fractional values. So I can say go from 0 to 10 in steps of 0.000002. Okay, so if I want to make ranges which aren't just integer values, it gives you arange gives you an easy way of doing it. And then what's this? So when I do this, I'm basically going to be creating a list of numbers, 50 million numbers, right? And now here I've got sign of x. So I'm telling it take the sign of a list. Normally in Python you can't do that. You can't say sign of 0.1, 0.2, 0.3 as a tuple or a list. It'll give you an error. It only takes single values. So NumPy actually redefines a lot of these transcendental functions, and the redefined versions can work with lists of values automatically. So there are a lot of things that you can do which wouldn't make any sense using the normal math library, but in NumPy they happen as you would hope they might happen. Look at that. 742 milliseconds, 478 milliseconds, 473. So again, you can see the first time it was a little bit slower because it was getting things initialized, and then half a second. So half a second, that's a heck of a lot better than 7.1 seconds. So NumPy is really good. So why couldn't Cython, which was compiling my Python code into machine language, do as good as NumPy? What's going on there? All right. So the fundamental issue that's causing things to be slow when you're doing mathematical operations like that in Python is one of the most powerful features of Python, which is that variables in Python or lists in Python can include arbitrary types of data. So in Python, if I say 5.0 times 10, it has to look at the 5.0 and say, okay, what kind of value is that? Is it an integer? Is it a floating point number? Is it a string? And then the 10, what kind of value is that? The integer, floating point, string, and then I have to treat it differently depending on what those different data types are. That's not how most programming languages work. In C, when you have a variable like x, when you declare the variable, you have to declare the variable, and you have to say what type of value that variable is going to contain. And it can only contain that type of variable. If you make a list, the list has to have all the same type of value in it. You can't mix strings and floating point numbers and that sort of thing. The price you pay in Python for that flexibility is it makes things a lot slower because it has to do a lot more checking while it's running. And that checking just takes a lot of time, as you can see, about a factor of 10. So what NumPy allows you to do is NumPy has a special type of object called the array. There's a couple other types of objects which are similar in functionality, and these array objects, unlike normal Python lists, can only have a single data type in them. So when you declare the array, you declare the data type the array contains, and then it can do math really fast and efficiently. So again, we have to import NumPy. After we've done that, here are a few different things that are available for these array objects. So let's create an array object. Oops. Okay, so here I'm creating a tuple, and then I'm using the array method to convert the tuple into a NumPy array. Okay, so now if I look at A is an array like that. I can treat arrays very much like lists in pretty much every respect. I can do slicing, I can do all sorts of other things, but there are also additional things I can do with them. So I can say A of 2, and I can get back element number 5. It'll behave basically exactly like a list in that sort of respect. This is also a good time to give you a warning. There is another library in Python, a standard library in Python called array. And if you have that array object does similar sorts of things to what NumPy does, but is far less effective and capable. If you accidentally have imported that array and then you try to use it like a NumPy array, obviously it's not going to work right. And when you do the importing, you can easily have a conflict between those two types. If you need that kind of array for one thing and you need a NumPy array for something else, then you need to make sure that you don't have the module conflict. So that's why doing import NumPy as NP is a better approach, because then when you would say np.array instead of just array. Anyway, back to this. So once we've defined our array, we can do all sorts of different things. Now, the array that I've defined here is just a one-dimensional array. That's another nice thing about this. In regular Python, if you want to have a two-dimensional array, the way you would do it is you would have a list of lists. So you'd have a list like, let's say I wanted to make a 3 by 3, I would say b is equal to now, this is fine, this works fine. You can access the elements using things like b of 2 of 1, like that, like we saw earlier. But this isn't a single object. This is actually a list of 3 other lists. So there are actually 4 objects in here. So accessing any of the elements in here is really inefficient and slow. If I turn this object into a NumPy array, you can see the presentation of it is different, and it's actually now just a single object, a single two-dimensional object. NumPy arrays can actually take n-dimensional data. So if you want to have a tensor, if you want to have a 3-dimensional array of data or a 4-dimensional array of data, you can do that. And NumPy will let you do all sorts of fun things with them. So since we can have these multi-dimensional arrays, we have to have some way of getting information about what shape they have and what size they have and that sort of thing. So that's where these properties come in. So if I say b.shape, b.size, okay, so the shape of the array is the dimensionality of the array. So it's basically saying the first axis is 3, the second axis is 3, and it only has 2. There's actually another one. If you could say len of b.shape, and that'll tell you how many dimensions it has. But then there's also ndim, I think. Yeah. So you can ask for the dimensionality of the array. You can ask for the shape of the array. So you can find out how big it is in the different axes. And you can ask for size. And size is the total number of values that are in the array. So if it's a 10 by 10 by 10, it'll give you 1,000. Let's see. Oh, yeah. And then the last thing here is dtype. So this is saying that the array that I've created here is an int64 array. So it is an array of 64-bit integer values. So back to our list here, you can see all of these different types that are supported here. Now, there are several different ways of specifying type to NumPy. The old style way of doing it is very much like we saw early in the printf, with the print statement with string formatting. You remember we had things like D for integer and F for floating point number. Well, the values aren't. Unfortunately, they're not the same values, but they are similar in construct. So F is a single precision floating point number. G is a long floating point number. Then you have integers of various lengths and that sort of thing. So this is a little counterintuitive to figure out. So it has this alternative representation. So I can say dtype int 8, something like that. Oops. And that would let me store, say, 8-bit integers. Yeah. Now, if I have an array, like our B array, which is an integer array, let's say I have some reason why I need to turn that into a floating point array. So I want to make this, say, single precision floating point numbers. Then I can say b.asType float 32. I think that'll work. Yeah. So float 32 would be a single precision floating point number. I could say float 64, and I'd get a double precision. And you'll note in the representation it prints out here. Here it just says 1. Here it says 1 dot. Doesn't have anything after it because the value is 1.0. But the dot indicates that those are floating point values. All right, so those are the very basics of dealing with NumPy arrays. Yeah, it's just a rehash. These are the various sorts of types that are typically used. Now, what other sorts of things can we do with these arrays? There are all sorts of different methods. So NumPy was written in 1995, I think, first. Oh, sorry. Originally, it was called Numeric, which was written back in 1995. Then they said that it was Numeric was a little too messy and freeform and stuff like that. So a bunch of people got together and they wrote NumPy, which worked pretty much like Numeric, but they organized it a little bit better. But even the better organized version still has strange naming conventions, and it takes a little getting used to. There's a steep learning curve in dealing with NumPy initially. Some things are really easy to do, but for example, if you wanted to read data from a text file that contained a bunch of numbers, how would you know to look for a built-in function in the NumPy module called load text? It's hard to find things sometimes, so it takes a little bit of getting used to. All right, so there are various ways of creating an array. We saw arange, which is equivalent to the range statement in Python, but lets you deal with non-integer values, and basically that creates an array object for you. Load text allows you to load values from a file. We'll talk about that in a bit. From function allows you to define a function and then use that function to create values in the array. Another very common way of creating arrays is with zeros. So if I say zeros of 5, it'll give me an array containing 5 zero values. If I say zeros 5, 5, it'll give me a 5 by 5 array, and I could say 5, 5, 5, and it'll give me a 3-dimensional array, but it'll be pre-filled with whatever value, pre-filled with 0, and then you can do things like, let's say, +1. And now I have an array of all 1s. So these arrays, you can use normal mathematical operations on them. So you can add values to them, you can multiply, you can do all sorts of standard mathematical operations. Yeah, question?
Is this the equivalent of like an empty list, or can you not manipulate?
It's not an empty list, it's a list that has zeros in every position. Right? So an empty list would be a list that had 0 length. So this is creating a pre-populated list of some size.
Okay.
Yeah. Now, one other important thing to realize here. So let's say I have okay, so now I have an array called 1 and an array called 2. And I mentioned that I could add, right? So I could say 1 plus 8, and it'll add that 8 to each value in the array. But I can also say add 2 arrays together, and what it will do, it's not going to be like a matrix or something like that. What it's going to do is it's going to add positionally each element together. Maybe I should do that a little differently. Let's say A is equal to array 1, 2, 3, and B is equal to array 4, 5, 6. So now I've got A plus B, and it will add 1 plus 4 to get 5, 2 plus 5 to get 7, 3 plus 6 to be 9, and I could also say A times B, and I could do something like that. So these are arrays of numbers. They're not matrices or something like that. These aren't vectors or matrices, where mathematics has a very different sort of meaning. However, NumPy does have those objects. When you create the array, you can actually also specify the type. I could add an extra option here and say int 8, and it'll give me an error. Should give me an error. Oh, why didn't it give me an error? Oh, interesting. So it rounded rather than yelling at me. Okay. So you can tell it what type you want to use when you create it if you want. Otherwise, it'll default to something which it thinks is sensible. Okay, so we were saying multiplication, addition, that sort of thing. Right. So it does have another type of object built in. So we've been using the array type. There's also a matrix type. So if I want to create a matrix, so this is actually from a later slide. We'll just do it right now. I say mat. And let's make. Let me go ahead and do another one. So let's do that. So now A is a matrix 1, 2, 3, 5, and B is a column matrix 1, 2, 3, 5. Okay. You can also transpose arrays. So if you have a two-dimensional array, you can transpose it, and that will make X, Y, and Y, X. But for a matrix, you can do it with vectors, right? So here I've basically defined a vector, and then I transpose the vector, so I get a vector in the opposite orientation. So now that I have a row vector and a column vector, I could say A times B, and I can produce the product, the inner product of the vector, and I could say B times A, and I can get a matrix out, and that sort of thing. So if you want to do real linear algebra, the matrix class is the way to go in NumPy. There are methods that you can use if you have an array rather than a matrix. There are methods you can use with arrays which will also do linear algebra sorts of things instead of value by value sorts of things. But if you're going to really be doing proper linear algebra, you probably want to use matrix instead. Right. I mentioned before you've got transcendentals. So if all right, let's do this. Sine of 1 over 2. Okay, so I can take sines, cosines, square roots of entire arrays at one time. Doesn't matter what dimensionality the array has. Transcendentals will work that way. There are also some funny sorts of operations like this. So if you didn't realize NumPy could do this, you would never predict that this would have been a feature of the language. What does this let you do? It allows you to create create an array which is a subset of the original array meeting some criteria. So let's see what happens. There we go. Okay, that's how you do it. You have to use the variable name. It's the name of the array itself inside the braces. So that allows you to select subsets of values meeting some logical condition or something like that. There's a method sort, just like the sort method for lists. There are some convenience methods for computing mean, standard deviation, other statistical properties. These are the methods I was saying that you could do matrix sorts of things with arrays. So there's an inner product, outer product, dot product, cross product, that sort of thing. And then there's a nice convenience method for computing histograms of values. You just have to give it the number of bins and the range that you want to cover, and it'll return a new array which has the results of the histogram. Okay, this is the matrix example that we just did. Okay. Now, if you want to read values from a file, there's a convenience function called load text and another convenience function called save text, which allows you to take a NumPy array or a set of NumPy arrays and easily read to a text file or write from a text file. I'm not going to go into any more details than that with this because it's involved in your homework, and I'm going to force you to read the documentation a little bit. Although I should say that this is only one way of doing it in your homework, and this may not be the easiest way, but it is one way you can do it. So you can read and write from text files. This is just a warning, which is when you read from a text file, the orientation of the data that you get back out may need to be transposed before it's the orientation that you want. Okay? You'll understand what I mean if you play with the method a little bit yourself, and you will have access to some appropriate text files as part of the homework assignment. All right, SciPy. We could spend an entire term going over SciPy. SciPy is a massive library of scientific mathematical calculations. This is not even a complete list of all the modules in SciPy. This is just a list of some of the more useful modules. So it has modules for doing things like clustering, Fourier transforms, integration, differential equations, linear algebra, maximum entropy. The list just goes on and on. Pretty much any topic that you might think of in math, there's very likely to be a module for this. So you're probably familiar with at least have heard of MATLAB, standard commercial package for doing matrix operations, math, that sort of thing. So you've basically got MATLAB, which is good for doing numerical calculations, and then Mathematica, which is good at doing symbolic work. So if you want to prove something, you'd use Mathematica. If you want to get a number out, you'd use MATLAB. And I will point out that Baylor has site licenses for both of those. So if you ever need Mathematica or MATLAB, you can get access to them for free. SciPy basically gives MATLAB-like functionality to Python. So the combination of SciPy and matplotlib, things we're talking about today, will allow you to do most of the things that you might want to do in MATLAB, even with all the various add-on modules you can get for MATLAB. It's really surprisingly complete. Now, the way SciPy came into existence was a company was formed to make SciPy right around 2000, I think, 2000, 2001, something like that. And they had an interesting business model, which was, well, we've got all these companies out there, and they're sick of paying MATLAB these $50,000 a year license fees. So maybe we can leverage that market a little bit. So what they would do is they created SciPy, and they put put NumPy and all the other open source software they could find for doing mathematical sorts of operations into it. And then they turned themselves into basically a consulting business. So if a company said, wow, I really like SciPy, but I really need to have clustering capabilities, and you guys don't have that stuff yet. Or I really need to be able to do sparse matrices efficiently, but you guys don't have that. That company could pay the company that makes SciPy to develop that library on the condition that it became part of the open source package from that point on. And it seems like a kind of a funny business model that might not work very well, but it's been going for about 20 years now. So it's actually been reasonably successful. And gradually over time, SciPy has gotten bigger and bigger and bigger. So now it's really the standard library that people use for doing mathematical sorts of things in Python. And it's completely free for end user use. The only time you really have to pay anything is if you want to pay them to add something to it. Okay, so again, we're not going to go through any of these libraries in any depth. It would just take many entire classes, and a lot of you are going to be doing things more like processing sequence data and stuff like that. This isn't a class on mathematical computing. It's a class on programming. But it has really good documentation, so any of these modules you can just go to help, or you can go to the online documentation. You can find out a lot about what they do. Now, So SciPy and NumPy and Matplotlib give you the ability to deal with matrix sort of data, array style data, where you're really just focusing on values. If you're dealing with data which is really spreadsheet data, so when you're dealing with something which is nicely formatted as a spreadsheet, but that may include text labels in addition to numerical values, and it may have different types of numerical values, including currencies, which have to be a fixed decimal point, and that sort of thing. There's another library out there called Pandas. Pandas, it has built-in tools for doing things like reading Excel files. Reading Excel files is not a trivial process in any way. It's a very complicated file format, but it can read Excel, OpenOffice, CSV files, that sort of thing. So it can read spreadsheet style data, and then it allows you to treat that data as arrays in various ways. So it allows you to access the data programmatically very easily. There are pretty good interconnections between Pandas and NumPy. So if you pull out a big list of values from Pandas, you can easily turn that into a NumPy array or something like that. Bottom line is, if the sorts of manipulations you're trying to do are spreadsheet-like, you should look at Pandas. If it's more just a set of values that you measured from some instrument or something like that, then you probably want to go with NumPy. Okay, that's it for the mathematical stuff.